All right, so if we're to recap linear momentum, we know P equals mv. So we're dealing with a mass with a certain velocity, and we have to have direction with that. So angular momentum, the angular momentum of a rigid body with a momentum of inertia I rotating about a fixed axis is given by L equals I omega. So we're dealing with now, instead of mass, we're dealing with moment of inertia. And instead of linear velocity, we're dealing with angular speed. So the greater the moment of inertia, in other words, the greater mass that you have or the greater radius that you have, the more moment of inertia that you have. And then angular speed, the faster something is spinning, the greater the angular momentum. And so it has to do with both things, how big the moment of inertia is and then how fast it's moving. And yeah, and so we could compare different objects. Let's say we had a bowling ball, and then let's say that we had a volleyball, right? About the same size, bowling ball, volleyball. This has much more mass, so if they're both rolling at the same rate, let's say they're both rolling at 4.3 radians per second, obviously this is going to have more angular momentum as it spins. All right, so let's consider a ball that's spinning. Remember, a point mass, the moment of inertia for a point mass is just mr squared, the mass itself, times r squared. We want to find the angular momentum. So it's going 32 radians in 1.7 seconds, and we'll assume a constant speed, and we want to find the angular momentum. So, it's pretty straightforward there, right? We have the point mass, which is r squared. Omega is how many radians we cover in time, and we get 18.82 radians per second. So when we calculate the moment of inertia, or the angular momentum, 0.418 kilogram meters squared per second. So yeah, pretty straightforward there. All right, so again, linear speed equals r omega. And so if we are looking at, what's going on linearly with a radius, and then we have the point mass there, we get mr squared v over r. And so then we'll get mvr, and that will give us the angular momentum. All right, so let's practice this one here. We have a ring, and moment of inertia for a ring is capital mr squared. It's the mass of the whole ring times the radius squared. And we know that the linear velocity is 2.5 meters per second. The radius is 3 meters. The mass is 16 kilograms. And we want to find the angular momentum of the ring. So go ahead and pause the clip and give us a try. And when you're ready to check, you can hit play to continue. All right, so V equals r omega. So it's spinning at 0.833 radians per second. And we can get the angular momentum, mr squared times omega. And we should get 119.952 kilogram meters squared per second. All right, now if we're changing the angular momentum, let's consider, that we are applying a force over a period of time, making the spin faster and faster over a radius, right? So torque equals force times radius. And we know that the change in momentum, the change in angular momentum, is a torque over a period of time. And so what we can do then is, if we look at this one here, if there's, let's say there's a resistive force of 6 newtons, how much time will it take to stop? Well, this is the resistive force, and we know that the change in angular momentum equals torque times time, and there's a 6 Newton resistive force. So for torque, that's force times the radius, and then we're looking for the period of time. The change in momentum would be L final minus L initial. So the final would be 0, the initial would be this, right? And so you could find how much time that is, and it would be 6.664 seconds. And yeah, so if you have a force over a period of time, similar to linear momentum, you can change what's going on rotationally, and that's what we see here. All right, so conservation of angular momentum. We know that when there is no net torque, the angular momentum must be conserved. And a classic example of this is a figure skater, right? So when a figure skater is spinning in the air, and let's say her arms are extended outwards, right? That means that I, which is the moment of inertia, is greater because even though the mass is the same, her overall radius is bigger. So when she brings her arms in, I gets smaller, the moment of inertia gets smaller, therefore something has to compensate. And that's where we're dealing with conservation of momentum, angular momentum. So L initial must equal L final. So in this case here, let's look at, A here. I is large, so we have a large angular momentum with a smaller, or I'm sorry, larger moment of inertia and smaller angular speed. But then afterwards, because this gets smaller, because the moment of inertia gets smaller, she must have a bigger angular speed, and so she's spinning around faster as she goes around. So if we practice this, let's say that she is spinning at 7.5 radians per second as she spins. Let's say the moment of inertia is 480 kilogram meters per second squared. What would be, if her new moment of inertia is 365, what would her new angular speed be? So go ahead and pause the clip and give that a try. When you're ready to check, you can hit play to continue. Okay, so I initial omega initial equals I final omega initial final, and so she'll be spinning now at 9.86 radians per second instead of 7.5, so she's going to be spinning faster. All right, let's practice an exploding star situation. Let's say that we have this star with mass m and it's rotating with a certain angular speed and it explodes mass into space. The star that's left behind has 1/10 of the mass and 1/20th of the radius, and we want the new angular speed. If you remember, for a sphere, as 2/5 mr squared, again, you don't need to memorize the moments of inertia. And let's say we want to compare these two. What we want to do is look at the new situation over the old. Again, another ratio setup here. Now, I'll have you go ahead and try this. What's going to happen to the new angular speed if this is what happens to the moment of inertia? So once you figure out what's going on with the moment of inertia, then you can look at conservation of angular momentum, L initial being equal to L final, and go from there. So go ahead and pause the clip and give this a try, and when you're ready to check, you can hit play to continue. All right, so we know that with a drop in moment of inertia, the angular speed must increase. Let's take a look at how the ratio works out, how things cancel from the top and bottom. And so we get 1/4000th of I, which is much, much smaller. So therefore, it would have to go up by 4,000. And so, yeah, that's quite a significant increase. All right, so for this one here, let's say we have a disk that's spinning, and we know how fast it's spinning, 3.6 radians per second. And let's say all of a sudden a clay mass falls on it, and we want to find the new angular speed of the disk. Well, if we think about what's going on initially and what's going on in the final spot, initially all you have is just a spinning disk. But afterwards, you have a spinning disk and you have that point mass, which is an mr squared. So what you're going to have to do in the afterward spot is deal with both, right? So let's go ahead and set that up. We have I omega over on this side. So we have the disk, which is 1/2 mr squared. And then on the right-hand side, we have the disk and we have the clay mass both. And so if we, and they'll have the same omega final. So we're dealing with both over here and just this over here, right? And so when we place our values in there, we can figure out what the new angular speed will be. And so, yeah, go ahead and pause the clip and finish this up. And when you're ready to check, you can hit play to continue. All right, so we've got those two. We can place our values in there. We should get a final angular speed of 2.72 radians per second. So it's going to be slower, which makes sense because the moment of inertia has gone up here. All right, now we're ready for our final problem. This is a snowboarding situation. So a snowboarder is in the air. She decreases her moment of inertia by 1/4 by bringing her arms in during a jump. if their initial angular speed is 2.6 radians per second, how much faster will they spin? So see if you can set up, what's going on before and what's going on after in a relative sense in terms of what's going on with moment of inertia. Give this a try, and when you're ready to check, you can hit play to continue. All right, so full moment of inertia starting out with a 2.6 radians per second turn, and then she's only 3/4 of the original moment of inertia. So what would the new, angular speed need to be? Well, if we set it up like that, where it's 3/4 I as compared to the original, we can solve for that, and she would have to be spinning then at 3.467 radians per second.